They claim the James Webb Space Telescope spotted a large object about 10 light years away moving toward Earth. The posts claim that the telescope captured the object changing its trajectory.
The James Webb Space Telescope just pulled off something absolutely incredible, capturing the first real image of 3I Atlas, an ancient interstellar comet that's been traveling through space for potentially billions of years. This isn't just any space rock. It's a chemical time capsule from another star system, carrying secrets we've never seen before. The comet's composition is so extreme, it's breaking everything we thought we knew. But what if this visitor is older than our entire solar system? What cosmic messengers are heading our way? Webb's historic capture, the first real image of interstellar comet 3I Atlas. The moment astronomers at the James Webb Space Telescope received the data on August 6, 2025, they knew they were looking at something extraordinary. Every pixel in that infrared image whispered stories of distant worlds, of a cosmic traveler that had journeyed across the vast emptiness between stars to visit our solar neighborhood. This wasn't just another space photograph. It was the first real image of 3I Atlas, an interstellar comet that had crossed unimaginable distances to deliver secrets from another stellar system directly to our doorstep. The discovery of 3I Atlas began in early July 2025, when the Atlas survey system detected something unusual moving against the backdrop of distant stars. This object immediately caught attention because it represented only the third confirmed interstellar object ever detected in our cosmic neighborhood. The first two visitors, Oumuamua and 2I Borisov, had already challenged our understanding of what might wander into our solar system, but both carried mysteries that left scientists with more questions than answers. Oumuamua defied simple classification with its strange acceleration and elongated shape, while 2I Borisov, though clearly comet-like, still left many questions about chemistry and origin unanswered. Now 3I Atlas was approaching on a trajectory that would bring it within reach of our most powerful telescopes, and the race was on to capture it before it disappeared forever into the cosmic void. This visitor was moving at incredible speeds, traveling roughly 210,000 kilometers per hour through space on a hyperbolic path that would take it past our sun only once. Unlike comets born in our solar system that follow predictable elliptical orbits, 3I Atlas was a one-time visitor, a messenger from distant stellar nurseries that would never return once it completed its flyby. Webb's technical masterpiece and precision targeting. The James Webb Space Telescope's successful capture of 3I Atlas represented a triumph of precision engineering and astronomical coordination that pushed the boundaries of what space telescopes can achieve. Using its near-infrared spectrograph, Webb managed to lock onto this faint-moving target across astronomical distances in what felt like threading a needle in the cosmic darkness. The technical challenge was immense, because from Webb's position at the second Lagrange point, 3I Atlas appeared as nothing more than a barely detectable speck racing against a shifting backdrop of stars. The team had to perform incredibly delicate calculations and precise trajectory modeling to ensure the comet would fall within Webb's narrow field of view, even as it hurtled inward toward the sun. Success required not just capturing an image, but obtaining a complete spectral map of the comet's glowing shroud, the coma that surrounds its nucleus like a ghostly atmosphere. This achievement demonstrated that space telescopes could track and study even the most elusive cosmic visitors with unprecedented precision. What emerged from Webb's instruments transformed our understanding of interstellar objects completely. The image revealed a dense carbon dioxide-dominated coma radiating in infrared wavelengths between 0.6 and 5.3 micrometers. This wasn't just a pretty picture, but a detailed scientific document that would revolutionize our knowledge of visitors from other star systems. Within that ethereal glow, Webb detected signatures of multiple molecular species, including water vapor, carbon monoxide, water ice, dust, and trace molecules such as carbonyl sulfide, each telling part of the story of this cosmic wanderer's origin and evolution. The technical specifications of Webb's observation highlight the telescope's revolutionary capabilities in ways that ground-based observatories simply cannot match. Operating in the cold, dark environment of space with unparalleled sensitivity in the infrared spectrum, Webb could tease out weak spectral lines, distinguish overlapping molecular features, and map brightness variations at fine spatial scale. Earth-based telescopes and even the Hubble Space Telescope struggle with sensitivity issues, background interference, and the inability to observe at long wavelengths where many crucial molecular signals hide. Chemical revelations from another star system. The chemical composition revealed in Webb's spectral analysis of 3I Atlas shocked astronomers with its extreme and unprecedented properties. The most striking discovery was the overwhelming dominance of carbon dioxide in the comet's coma, with roughly 8 times more carbon dioxide than water vapor present in the glowing gas envelope surrounding the nucleus. This ratio ranks among the highest ever recorded in any comet, forcing scientists to completely rethink how this cosmic visitor formed and evolved during its long interstellar journey. In typical comets from our solar system, water ice sublimation dominates as they approach the Sun, creating the familiar bright tails and halos of particles we associate with these celestial visitors. But 3I Atlas behaved completely differently, with its relatively weak water signal hinting at something preventing heat from penetrating deep into its interior. Perhaps an insulating crust of organic materials or an internal structure that slows thermal conduction keeps the water-rich layers frozen, while carbon dioxide and carbon monoxide, which sublimate at much lower temperatures, drive the observed activity. This chemical fingerprint becomes a direct record of the comet's formation history, one that likely echoes conditions in a stellar nursery completely different from our own Sun's birth environment. The balance of dust, gas, and ice in 3I Atlas's coma tells a story of formation processes that occurred around a different star, under different temperature and pressure conditions, in a protoplanetary disk with its own unique chemistry. If 3I Atlas indeed formed near a carbon dioxide ice line in its parent system, the environment around its birth star must have differed drastically from the conditions that shaped comets in our solar system. Beyond the dominant carbon dioxide signature, Webb's spectral analysis revealed a complex molecular inventory that includes water vapor, carbon monoxide, water ice, various dust components, and trace species like carbonyl sulfide. Each of these molecules contributes to our understanding of the formation conditions and subsequent processing this object experienced during its journey through interstellar space. The presence of these diverse molecular species suggests that 3I Atlas retained significant chemical complexity despite the harsh environment of the cosmic void. The spatial distribution of these emissions provides crucial clues about the comet's internal structure and activity patterns. Webb's images show that gas emission appears to occur broadly across sunward-facing regions rather than from isolated jets or specific vents. This widespread activity pattern suggests either a highly porous internal structure that allows heat to penetrate efficiently or multiple active regions distributed across the surface, each contributing to the overall outgassing observed in the coma. Physical mysteries and structural puzzles. Determining the exact size and structure of 3I Atlas has proven challenging, with current estimates placing its diameter somewhere between 1.4 and 5.6 kilometers across. This uncertainty in size carries profound implications for understanding the comet's behavior, because radius directly affects surface area available for outgassing, thermal penetration depth, and internal heat conduction processes. The size uncertainty also complicates efforts to calculate the object's mass and density, both crucial parameters for understanding its structural integrity and resistance to various forces. What makes 3I Atlas particularly puzzling is its apparent immunity to the recoil effects that typically affect active comets. Despite clear evidence of vigorous outgassing creating its substantial coma, the comet exhibits almost no measurable non-gravitational acceleration. In typical comets, jets of evaporating gases create thrust that slightly alters orbital motion, but 3I Atlas appears sufficiently massive or structurally rigid that these forces fail to perturb it detectably. This suggests either extraordinary density, strong internal cohesion, or a specialized structure that suppresses asymmetric thrust effects. Some analyses have estimated the comet's mass at over 33 billion metric tons, though these calculations carry large uncertainties due to the difficulty of measuring such parameters from Earth-based observations. If accurate, this would place 3I Atlas among the more massive comets known, potentially explaining its resistance to outgassing perturbation. A nucleus toward the larger end of size estimates, several kilometers in diameter, would carry sufficient inertia to resist the modest thrust produced by escaping gases. The comet's hyperbolic trajectory represents one of the most dynamically extreme orbits ever recorded, confirming its interstellar origin beyond any doubt. This path cuts through our solar system at tremendous speed, taking 3I Atlas on a one-time flyby that will never repeat. The trajectory analysis points back toward the constellation Sagittarius as a general origin direction, though tracing a comet's specific birth star after potentially billions of years of galactic motion remains nearly impossible. The early activation of 3I Atlas adds another layer to its structural mysteries. Unlike most comets that remain dormant until approaching well inside Jupiter's orbit, 3I Atlas began showing clear signs of activity at much greater distances from the Sun. This abnormal behavior suggests that volatile ices with very low sublimation thresholds began evaporating even where solar heating remains weak, implying either unusual surface composition or specialized internal mechanisms that remain poorly understood. Ancient wanderer from deep cosmic time. The story of 3I Atlas stretches back through unimaginable cosmic time, with some estimates suggesting this interstellar wanderer may be between 3 and 11 billion years old, potentially predating our entire solar system. If these age estimates prove accurate, 3I Atlas would represent a fossil from the galaxy's early epochs, carrying within its frozen core chemical memories of stellar environments that existed when the Milky Way was younger and perhaps dramatically different from today's configuration. The comet's exceptional velocity of approximately 210,000 kilometers per hour surpasses both Oumuamua and 2T Borisov, implying a more ancient origin and a correspondingly longer interstellar journey. This tremendous speed suggests that whatever gravitational event ejected 3I Atlas from its parent system was particularly violent, perhaps involving close stellar encounters, massive planetary migrations, or the disruptive influence of passing binary star systems. Such dramatic ejection mechanisms tell us that interstellar comets are not gentle wanderers, but survivors of cosmic catastrophe. During its eons-long journey through the interstellar medium, 3I Atlas would have endured a harsh gauntlet of cosmic challenges that would destroy weaker objects. Cosmic rays would have bombarded its surface, potentially altering its chemical composition through nuclear reactions. Micrometeorite impacts would have gradually eroded its outer layers, while thermal cycling from encounters with stellar radiation fields would have stressed its internal structure. The fact that 3I Atlas retained sufficient volatile reserves to remain active today speaks to remarkable structural integrity and perhaps protective mechanisms that shielded its interior from the worst effects of interstellar exposure. The comet may have passed through molecular clouds during its journey, regions of space where gas and dust densities are much higher than the typical interstellar medium. Such encounters could have added material to its surface or altered its composition through chemical interactions with the surrounding environment. Some of the organic compounds and trace species detected in its coma might reflect these interstellar processing events rather than original formation conditions. The survival of deep volatile reservoirs within 3I Atlas provides a unique opportunity to study primordial materials that have remained relatively unaltered for billions of years. Unlike comets in our solar system that have made repeated trips past the Sun, gradually losing their most volatile components, 3I Atlas preserved its original chemistry in the deep freeze of interstellar space. When we analyze its coma composition, we're essentially reading a chemical memory book written in an ancient stellar environment far from our Sun. Coordinated Multi-Observatory Campaign. The study of 3I Atlas represents one of the most comprehensive multi-observatory campaigns ever mounted for an interstellar visitor, with telescopes around the world and in space coordinating their efforts to capture every possible detail of this rare cosmic messenger. This collaborative approach proved essential because no single instrument could provide all the necessary information to fully characterize such a complex and rapidly changing object. Each observatory contributed unique capabilities and wavelength coverage to build a complete picture of this visitor from another star system. Hubble Space Telescope made crucial contributions with its July 21, 2025 observations, when 3I Atlas was approximately 277 million miles from Earth. Hubble's images revealed a distinctive teardrop shape in the dust cocoons surrounding the nucleus, providing essential information about dust distribution patterns, mass loss rates, and tail geometry that complemented Webb's detailed chemical analysis. The visible light perspective from Hubble helped scientists understand how dust particles interact with solar radiation pressure and how the overall coma structure evolves over time. Ground-based observatories like the Gemini South and North telescopes have continuously tracked the changing tail structure and overall brightness as the comet approaches the Sun. These Earth-based observations provide the temporal coverage necessary to monitor rapid changes in activity levels and tail development that space telescopes, with their limited observing time, might miss. The combination of continuous ground-based monitoring with high-precision space-based spectroscopy creates a comprehensive observational dataset unprecedented for interstellar objects. Archival mining played a crucial role in extending the observational baseline for 3I Atlas far beyond its official discovery date. After astronomers first identified it in July 2025, they searched through previous sky survey data and found the comet in images taken weeks or even months earlier, when it was much fainter and further from the Sun. This retrospective detection allowed scientists to track the comet's behavior over a longer period and better understand when its activity first began, providing crucial constraints on sublimation thresholds and thermal properties of its nucleus. The coordination required for this multi-observatory campaign demonstrates the importance of rapid communication and flexible scheduling in modern astronomy. When 3I Atlas was first identified as an interstellar visitor, observatories around the world quickly adjusted their observing programs to accommodate target of opportunity observations. This responsiveness proved crucial because interstellar objects move through our solar system so quickly that delayed observations might miss critical phases of their evolution. Polarimetry and unexpected chemical discoveries. Polarimetric studies of 3I Atlas have revealed some of the most unusual optical properties ever recorded for a comet, adding another layer of mystery to this already extraordinary object. Recent measurements of how scattered sunlight becomes preferentially aligned show that 3I Atlas exhibits an unusually deep and narrow negative polarization branch with the degree of negative polarization reaching about 2.7% at small phase angles and inverting around 17 degrees. This combination of deep negative polarization at low angles plus a narrow inversion angle is extremely rare among both asteroids and comets within our solar system. These unique polarimetric signatures suggest that the dust grains in 3I Atlas's coma have distinctive scattering properties that differ significantly from typical solar system materials. The grains might be unusually small, have particular surface textures, or exhibit high porosity that affects how they interact with sunlight. Such polarimetric traits may place 3I Atlas in a completely distinct class of object, further widening our understanding of the diversity of interstellar visitors and the range of formation environments that exist around other stars. Water detection in 3I Atlas required careful analysis using ultraviolet observations from the Neil Gehrels Swift Observatory, which identified emission from oxygen radicals often associated with water sublimation. These observations yielded an inferred water production rate of roughly 40 kilograms per second at a distance of about 3.5 astronomical units from the Sun. While this water signature remains faint relative to the dominant carbon dioxide outgassing, it represents important confirmation that water ice exists within the comet's nucleus, even if it contributes less to the overall activity than in typical solar system comets. The water detection suggests that at least approximately 20% of 3I Atlas's surface might already be active at its current distance from the Sun, representing a surprisingly high fraction compared to many comets in our solar system. This widespread activity could result from the presence of large icy grains in the coma that act as extended sources of water vapor, releasing molecules well away from the nucleus surface as they sublimate in the solar heating environment. Perhaps most intriguingly, some telescopic campaigns have reported the detection of nickel in 3I Atlas's coma, a metallic component seldom emphasized in typical cometary studies. The presence of nickel indicates that a fraction of the dust being released carries metallic or refractory inclusions, possibly pointing to formation or processing in high-energy environments involving shock heating or metal-rich phases in protoplanetary disks. This metallic component, combined with the extreme carbon dioxide dominance over water, creates a chemical profile unlike anything seen in solar system comets. Future evolution and critical observation window. As 3I Atlas continues its journey toward closest approach to the Sun, in late October 2025, scientists anticipate dramatic changes in its activity levels and observable properties that could reveal entirely new aspects of this interstellar visitor. The comet's current distance of about 3.3 astronomical units from the Sun represents only the beginning of what should be an increasingly spectacular display as solar heating intensifies. New volatile components may reach their sublimation threshold, potentially revealing molecular species that remain hidden in current observations and dramatically altering the composition of the coma. The major challenge facing astronomers is that the most critical phase of 3I Atlas's evolution will occur when the comet passes behind the Sun from Earth's perspective, creating an observational gap precisely when the most interesting changes are likely to occur. This solar conjunction will hide the comet from terrestrial and near-Earth space telescopes during the period of maximum heating, leaving scientists to rely on solar-orbiting spacecraft and indirect measurements to monitor its behavior during this crucial phase. This observational challenge makes Webb's current baseline observations all the more valuable as they provide the benchmark against which any post-perihelion changes can be measured. If 3I Atlas undergoes significant structural changes, releases new volatile components, or experiences fragmentation during its closest approach to the Sun, these alterations will be detectable only by comparison with the detailed chemical and structural information Webb captured during the pre-perihelion phase. The comet's tail has already begun showing dramatic growth and evolution in ground-based images from observatories like Gemini South, with evidence of accelerating dust and gas loss under increasing solar influence. As this tail continues to extend and evolve, its morphology will provide crucial information about dust particle sizes, gas dynamics, and the interaction between different components of the coma. The curvature, opening angle, and brightness distribution within the tail encode information about radiation pressure effects, particle velocities, and mass loss rates that will help scientists understand the comet's internal structure and composition. Thanks for watching another episode. While you are still here, make sure to click the video on your screen for more quality content.